Neil Farmer, Executive Directors at Consulting Engineers, Tony G and Partners. Today I'm talking about how we use fibre reinforced polymer composites for strengthening concrete metallic structures. As it says on the slide, I'm Neil Farmer. I'm one of the Executive Directors at Tony G and Partners. We're consulting engineers. We've been extensively involved with steel plate bonding from the early 90s, but it's fair to say since about 1996, the use of steel plate bonding has been largely superseded in the UK by structural strengthening with fibre reinforced polymer composites, and that's what I'm going to talk about this afternoon. Hopefully at the end of about 35 minutes you'll understand what FRP composites are. I'll talk about the material properties and the forms of components that are available to us, why we need them, give some strengthening applications and their advantages, talk a bit more about how we install them, just reiterating some of what Mark said with regard to the adhesives and the concrete preparation, but also talk about some of the differences. So we'll talk about how we install them, again focusing on the different types of FRP materials and the locations that we can use them, and give some case studies, not only for concrete, but we've also used composite materials to strengthen cast iron structures. And I'll no doubt there's quite a few designers in the audience here, so I'll just tell you what design guidance is available and just talk about some of the differences in structural behaviour compared to, say, reinforced or pre-stressed concrete. And again, just touch finally on some of the inspection and testing techniques. First of all, what are fibre reinforced polymer composites? If I was giving this talk back in 1996, then probably most people wouldn't have known even what carbon fibre was, unless you happen to be a golfer like me. But now the carbon fibre in particular is extensively used in sports goods. Formula One cars are all made of these materials. We also use glass fibre reinforced composites for things like boats, and certainly aircraft make extensive use of the materials. For construction applications, we use them for external reinforcement, strengthening structures, largely replacing what we would have used for steel previously. Composites, quite simply, composite material is just a mixture of a hardened matrix and a reinforcement. Timber, natural composite, exactly the same. It's got fibres in it and a matrix. And reinforced concrete, we've got a concrete as the matrix and steel as the reinforcement. With fibre reinforced composites, we've got a resin for our matrix, largely epoxy we tend to prefer, but we've also got a fibre which can be woven into a fabric. Three principal types of fibres that we use: carbon, aramid, which some of you may know as Kevlar under its trade name, manufactured by DuPont, or there's Twaron as well, or glass fibres, which if you're making a boat, probably make it out of glass. But largely the great thing is different composites can be manufactured to have different properties. In terms of the fibres that are available, so this is our reinforcement. There's three principal types that we use. I think Chris mentioned basalt fibres this morning. That's true. Basalt can be melted down and made into a fibre, would you believe? But it's not quite as extensively used, certainly not for external strengthening purposes as the other fibres. Principally, this is an aramid fibre. You can see it's a yellowy orange colour. This is what they use in bulletproof vests. It's a very soft material, got to be to stop bullets. You really struggle to cut it if you try and cut this with some conventional scissors, or you'll just blunt it. Then we have our carbon fibres, which is notable because it's black. Carbon only comes in one colour, I'm afraid. And that is the most commonly used material for strengthening purposes, largely because it's strong and it's stiff, and it also happens to be lightweight like the other fibres. And then we have the cheaper fibres, so if we've got bulk quantities that are needed, so a wholly FRP composite bridge, for example, is likely to be made out of glass. It sort of does the job, but it's if we're using it in thin materials like you'll see in a minute, it's better to go for carbon. Resins, Mark's touched on the various forms of resin. I'll just mention the top one now, which is phenolics, which some of you may not be quite as familiar with as the others. Phenolics are used particularly where good fire resistance is needed. So quite often, for example, if you're strengthening, say on a London Underground application, you're likely to have used at least a phenolic coating over the composite materials at the end to try and stop it catching fire, stopping the toxicity that can come from some of the adhesives, and just preventing excuse me, flame spread. Polyurethanes, polyesters, vinyl esters, you may have come across these, but it's the bottom one there, epoxy, again, is the one that we tend to use. We concentrate on that for reasons that were given in Mark's presentation. We can take the fibres and manufacture them into certain components. The most commonly used component in the UK has been what we call pultruded strips. So this is basically taking carbon fibres, which each carbon fibre is only 5 microns across, so you literally have to bundle thousands of them together in order to sort of be able to form them into anything. So what they do is they combine them into what are called tows or rovings. These are only quite thin themselves, and you can then use these to either weave the materials, which I'll talk about in production of fabrics in a minute, or you can pull them through a bath of resin, epoxy resin, heated, compact them through a dye, and then, say, bake them at quite a high temperature and ultimately prepare the surface for bonding. And so you can get some, it's almost, I think generally about 250 metres is the sort of length that they tend to get produced in. And that's been commonly the most common form of strengthening we've used in the UK, certainly. Alternatively, you can weave the fabrics or weave the tows into fabrics. Again, all the three fibres I mentioned can be woven. Then you can take your fabric and use that as your external reinforcement by either dipping the fabric in a bath of resin and then applying it to your concrete structure after suitable surface preparation, or you can apply resin to the structure directly and then apply the dry fabric onto the structure and build it up into layers to the required requirement. So I guess in addition to having high strength and stiffness, one of the main advantages and characteristics of composite materials is the fact that they are so light. Typically in density terms, you're looking at 1/5 to 1/4 that of steel. And the fact is, we need a lot less cross-sectional area to give the same strength as well. So needless to say, the guy on the right here just applying one plate was literally, you probably got a mate over this end, but that was it. 2 guys can quite happily apply quite a long plate. And you can see here craneage for a whole FRP. This is a glass fibre reinforced bridge. It can be considerably reduced as well. So there's obvious savings associated with lightweighting. From an engineering point of view, the materials are also great because they're linear elastic, so fairly easy to predict. Constant stress-strain relationship. On the downside is they don't have a yield platform, so you need to be very careful at your operating level of strain because you won't get very much notice of failure. If indeed you were to fail the composite, more commonly you're likely to be limited by the bond to the material, be it concrete or steel. Mark's already touched on why we need these sort of materials, so I won't dwell again on these, but other than to mention the bottom one there is something that's become more prevalent in recent times. Is not only are we concerned about maybe impacts to structures, maybe vehicles going through parapets or whatever, but also more recently the need for sort of blast protection, either intended blasts, a terrorist bomb or gas explosions. We can often use the materials to strengthen against those loadings. In terms of why we need the materials, most of this morning's presentations were concerned about how the management and treatment of corrosion. But if you can actually eliminate corrosion, then you've got a major gain. And that was really the driver for composite materials, not from construction industry. It generally came from more applications, sort of marine and aerospace. But if you can resist the normal deterioration processes of our conventional materials, say wood, steel, concrete, then there's clear gains to be made. And that was really the sort of the raison d'etre for their being invented in the first place. So to date, they don't really have any significant, they don't really suffer significant deterioration due to conventional environmental actions, other than to say they do have resin in them, and therefore ultraviolet light is something that does need considering. You can get UV stabilised resins as well to deal with that if you have got a structure that is exposed to direct sunlight, but other than that, they're significantly more environmentally friendly. Ultimately, they're light, strong, stiff and durable, and that's why they're used so extensively now. So the more obvious or not so obvious advantages, clearly if we're going to actually retain structures and we're not going to have to demolish them, there's going to be savings, both in terms of materials, obviously cost as well, but in terms of installation, because they're so lightweight, there's both health and safety benefits, but also speed of application. These two guys on the right are holding a plate that's about 10 metres, between 10 and 11 metres long. Now, even if that was in steel, you'll probably need a small army of people to lift that into position. And the fact that you've got a strength weight to rate ratio 60 times that of steel clearly indicates you're going to be using a lot less material. One of the big savings is in time for installation as well, because they're lightweight and they're also flexible and easy to manoeuvre around existing structures. The position on the photograph on the left there is the Loudwater Viaduct on the M4 at Wickham, where there was 6.6 kilometres of plate applied to the top surface adjacent to live traffic, but as you can see there was really no mechanical plant at all. It was all just applied by hand. And on the right here, this is a twin cell culvert down in Devon, where the actual roof slab of the culvert was to be strengthened, but it was I think it was about 100 yards away from this opening, so it had to be taken down and applied some distance, and that would have just been impossible with steel plates. Also, they're aesthetically neutral. You can apply them to the bottom, the soffit of a structure, such as this bridge. You can see they're black on black, so there's actually they're not really noticeable at all to people other than probably engineers. But also on Tower Bridge, on the light standards, and some of these standards, they've been strengthened with composite materials, and yet the general public wouldn't know that just looking at them. And because they don't need any mechanical plant to erect them, they're obviously things can take place a lot quicker, so there's reduced disruption. We don't need long possessions. You can often apply the materials to the soffit of a structure while it's being used, subject to certain vibration criteria. Say no large noisy plant or equipment. Any dust in the preparation of the substrate can be contained. There's plant that has vacuum extraction attached to it. and clearly if we're training there's no demolition risks. All of the preceding slides really add up to the fact that the whole process of installation and strengthening by FRP plates is a lot cheaper than conventional means. One of the big gains really is the fact that you haven't got to divert utilities, particularly in the case of bridges. You know, I've been involved in projects where utility diversion costs have been in the order of £2 million, and we've been able to just mitigate against those by strengthening the structure with composite materials. And ultimately there's minimal maintenance required, unlike probably for metallic strengthening. Just talk about how FRP composites are installed. The preparation of the concrete substrate, or could be steel as well, is exactly the same as for steel plate bonding, where we grip blast the surface of the concrete and remove any dust. Undertake similar sort of testing as well, pull-off testing, to make sure we've got the correct surface preparation. Then the strips themselves tend to come to site in a big roll, saying that's unveiled on site, and then the strips cut to the required length with a guillotine. I stress with a guillotine, not with a hacksaw, because it is the strips are, all the fibres are in one direction, and therefore you need to be a bit careful you don't split them longitudinally. But with the correct material that can be, correct equipment that can be done. Then similarly for steel, we need to clean the plates, particularly to remove any carbon dust. This should be done not with white spirit, because that can leave a residue on the surface, but there are proprietary cleaners that the likes of Sika have available to undertake this. Then when we mix the two-part epoxy adhesive correctly, the adhesive is applied into a bath. It's usually between two timber formers, which is what's happening here, and you can see the strip is being pulled out of the end. This former here, which is here, is actually produces a dome shape on the adhesive, so that when it's eventually applied to the structure and a roller is used to roll the adhesive out towards the edges, no air is entrained in the centre of the strip. So we want a substantially void-free adhesive layer. This is the strips being installed. The concrete's clearly been prepared, just like for steel plate bonding. An adhesive layer, typically about 2 millimetres thick, applied onto the concrete, and then the strips are offered up as they're doing there, and a roller rolled down the middle. You have to be careful not to over-roll it and draw air back into the joint. Some people actually put a warning sign on the strip as well, so that people don't come along and start drilling through it as future trades follow, particularly in the building trade. So I'll just give you some applications. I think these are all our projects actually, but sort of just show you some of the different applications that can be used. First is Calverley River Bridge. This is in Leeds, over the River Aire. There's a quite nice open spandrel arch. I think it's on the outer ring road. And two of these arches required shear strengthening. So this was actually the first application of a shear strengthening job in the UK with composites. So we had to, first of all, there was some conventional concrete repairs done that you can see there, just to make sure that the surface was nice and smooth. And then in this case it was fabric, because we were going to wind this around the arches, brought to site similar to the strips, cut to the right length. And then this was a dry applied process, so resin was put onto the structure, the adhesive, and then the dry carbon fibre offered up, and then you'll see here there's a washer roller, metal washers on the roller, forcing the dry fabric into the adhesive and fully wetting out the composite, and then subsequently further layers of adhesive applied by or the resin applied by brush, and more layers of carbon fibre. So this was built up by a process known as contact moulding, and ultimately ended up with the arches completely encapsulated with carbon fibre at certain points. And then subsequent to this, there was just a cosmetic layer put on the top to disguise it. This is the final structure. You couldn't actually tell. There's no difference between the ribs that have been strengthened to those that haven't. Ultimately, they achieved 55% strength gain on one of the ribs and 5% on the other, which was the target we were looking for. This is a slightly different application in so much this was a cast iron bridge, and you can see the original railway that ran under this bridge in the middle of Mould in North Wales. Somewhere along the line, somebody done an assessment and decided that actually the bridge couldn't take the loads and installed a propping system in there. I think that was done in the late 50s, early 60s. But actually in some of these, it was barely in contact with the bridge itself, so it wasn't actually doing an awful lot. So our brief was to upgrade it to full assessment loading. And we did this by using ultra-high modulus carbon fibres. These are the fibres themselves have a modulus in the mid-600s kilonewtons per millimetre squared. When combining a composite, you've got an E value of at least 360 kilonewtons per millimetre squared, so substantially stiffer than steel. And they were bonded onto the surface. They can be quite thick. I think in this particular case, we've done them up to 37 millimetres thick. That's probably the most extreme end of what you want to go to. And so at the end of it all, we'd managed to increase the bridge capacity from taking 17-tonne vehicles to 40-tonne vehicles, and also we'd allowed the client to remove the props as well and open both carriageways underneath the bridge, which no longer had a railway in it, but did connect two car parks. Here in London, opposite the opposite bank to the House of Commons, we've got St Thomas's Hospital. Did a quite extensive refurb job on that, and one of the mechanical engineers wanted to drill quite a lot of holes adjacent to a column. It was a flat slab construction, so you had maximum shear and punching shear and maximum bending just at the locations that we wanted to drill the holes. But we used FRP, you can see here, crossing in two directions to apply external strengthening, effectively replacing that lost reinforcement. Another building application, Alders department stores down in Croydon and Portsmouth. There was remodelling of the layout required. I think it was either a lift or an escalator, and a large void was formed in the floor slab, redistributing bending moments to adjacent panels, and we used FRP strengthening to increase the flexural capacity of those panels. The big thing here was that they couldn't afford to close the store because obviously they'd lose a lot of money. So all the works had to be done out of normal trading hours, and they had to apply the strips over the top of suspended ceiling units and fixings and other sort of suspended services. You can see the wires dangling from the ceiling here, and you can see the FRP strips that were installed. Say that would have again been impossible to do in those circumstances with steel plates. And another building, cutting holes in slab. This was a grade 2 listed buildings in South London. 1932, it was a health centre actually used for training the British Olympic team, the British swimming team back in the 1930s. But in 1999, it was converted into more luxury apartments. It was quite a historical building, that it was, the column crossheads were very similar to the Boots building in Nottingham, which was a slightly iconic reinforced concrete building. And so here what we did is apply strips on the bottom of the slab, which also had a cork installation, which is what you see. And then they were going to cut holes here for some nice spiral staircases. And unfortunately, in more recent times, we've had quite a few terrorist attacks in the UK as well. So there has been applications where we've used composite materials, particularly the aramid, to strengthen masonry structures for protection against blast. Obviously, you get a lot of potential shrapnel arising from the masonry. So as a designer, it's you know, say the materials do need to be fully understood if we're going to design with them. So make the first bullet point here, the important thing is don't think that they're just a substitute for concrete and steel and other traditional materials. You can't use conventional codes of practice to design with them on their own. You can adapt those codes and in combination with other advice, but they need to be considered as a unique material that they are. And fortunately there is specialist advice available here in the UK. Over the last decade and a half, we've produced some very good design guidance. The Concrete Society has produced 3 editions of Technical Report 55, 3rd edition in 2012, so it's reasonably current. Syria have also produced a similar sort of guide for strengthening metallic structures. ICE sort of started the ball rolling sort of around about 2001. But that has largely superseded that design guidance document. And overseas organisations have also produced their own. One in particular is the FRP. Back in about 2001, I think it was, produced a design guide. And that has been the basis for some software, some conceptual design software that Sika have produced. And I believe if you give your contact details and email addresses to Kerry on the reception afterwards, then you can sign up for to get that software. I would stress it is conceptual, it's not up to date with TR55, but it is a good first step. There's also been best practice developed on some other projects. There's MMS6 is one that was funded by the DTI, and really this has dealt more with the materials, the classification of quantification of composite materials for civil infrastructure. So again, there's information out there on the CompClass website. Just to give you a bit of an insight as to differences between how externally bonded strengthened structures behave compared to conventional RC. You've obviously can fail in compression if you don't design against it, or reinforcement yield, and concrete shear. All we're used to these concepts, but we do need to think more about what happens towards the end of the plates in these zones where you've got potential longitudinal shear stresses that could cause debonding of the plate if we don't take care to design against them. This here is an extract from Technical Report 55, TR55, and they highlight all these design considerations and tells you how to design against them. The 2 I'm just going to highlight here. One is shear crack induced separation. So as it says on the can, it's areas where you get high shear, and also longitudinal shear stresses in the yield zone. If there's areas, when you get to the point that the stresses in the steel reinforcement are nearing yield, you then get almost disproportionately high interfacial stresses along the bond line. I won't bore you with the mathematics, but it's sort of expressed in this diagram down here. So that obviously is an area that we need to look at very closely, and TR55 deals with that. So if you just draw a bit of a graph to try and demonstrate what's doing the work at any point in the loading cycle. This is obviously a sort of a flexural strengthening scheme. In most cases, we're probably not going to remove dead load, or not very much of it. So when you put your FRP composite on, it doesn't have any stress in it at all, or any strain. And then as you start and apply your load, increase the bending moment, the steel reinforcement is starting to strain more, and the composite is starting to strain more. And they're both working together until this point, at which point the steel reinforcement says, I've had enough, I can't do any more. You're on your own, FRP. And at this point, every increment in the loading cycle is taken by an increase in strain in the FRP. So you need to be a bit careful that you're not operating in this zone under normal working loads, otherwise your deflections are going to get very high. And if you do need that sort of degree of strengthening, then really what Fabio is going to talk next on post-tensioning systems is probably something that should be considered. Just give you a bit of information on the latest improvements to TR55. The main one is that it's been brought into total alignment with Eurocodes. They didn't exist in the earliest versions. So that's the major change. But also, in the meantime, we've had improved analysis and design methods. Some areas we had limited design guidance available before. Also, new materials and techniques have come along. And where there was slight disagreements on approaches, we've been able to rationalise those in some areas of strengthening. And just generally, everybody's a lot more experienced now, and therefore there's been a desire to maintain TR55 as the state-of-the-art document, I would say, rather than just a state-of-the-art document. Just sort of 3 chapters I'll mention in particular. Main structural design of strengthened members. Again, mentioned that we brought the load factors up into alignment with the Eurocodes, introduced fire resistance and fire engineering into it, and outlined design principles for impact, blast and seismic retrofit, which weren't really covered in earlier editions. If you leave things long enough, you'll start and gain experience. Things will happen to structures, and we've had some real fires in FRP strengthened structures. So we now know what we knew really from the laboratory, that at the sort of temperatures, you know, if you're up well beyond 300 degrees C, then by and large the resin is going to decompose, and therefore the strip is going to become ineffective. Your loading may also be lower, almost certainly will be, because some of it might have been even burnt away. But so you can use reduce factors in these situations, but you do have to be a bit careful in the fire situation. And also strengthening members in flexure, so it's bending analysis. There's a revised debonding analysis in the new version. Also introduced near surface mounted, that's NSM strengthening, which Mark will talk about, so I won't steal his thunder. But that basically involves introducing square or rectangular bars or even short strips into grooves in the surface of a member. So it's not really external strengthening, it's more internal, but it's dealt with in the document. And also touches on strengthening pre-stressed concrete beams. And finally, but not least, chapter 7 is strengthening axially loaded members. So this is columns or piers, you and me. There's been quite a bit of discussion on what was the best stress strain concrete model to use for this, and so there's been some rationalisation there in the confined concrete model that is included in the document. And this also deals with bending and axial loads, so combined effects. And there's also been a review of how we deal with rectangular column strengthening. This isn't quite as efficient in a confined model as circular concrete members, which are a lot easier to confine because the confinement comes at the corners. And so we've done some larger column tests. Here you can see what happens if you confine or don't confine concrete and crush it. What tends to happen is this is an unconfined concrete that's been tested to failure under axial load, as you can see, and this is a confined. Now the failure load on this column is a lot higher. You know, it can be up to 10 times higher, the failure load on this, with sufficient reinforcement. However, you do need to consider that this column is also now shorter than that column. They started the same length. So there's quite a lot of axial shortening as this gradually becomes a bag of rubble. And just to show that we really did do some combined axial and bending tests, this is quite extreme bending moments applied onto this column that had been confined. And you can see quite remarkably the steel has clearly yielded. It's not springing back, that. But it's got, quite reassuringly, the whole thing hasn't actually failed. So, you know, it's still capable of taking a vertical load, even under quite extensive P delta eccentricities. In terms of inspection and monitoring, talked about TR55. There is also a sister complementary document called TR57, which deals with how you inspect and monitor these materials. And so you should be aware of that document, very good guidance in there. Some of the techniques, I think we've talked several times about hammers today, got a bit of a thing. Usually we use, similar for steel plates, a very lightweight hammer can be applied to test, and to the trained ear you can usually determine if there's voids, but not always. There is a more sophisticated piece of equipment that Mark will talk about at the end of the last session that actually enables us to apply a known weight and sort of momentum and then capture the data from that. So that's probably a bit more sophisticated. And then we've got all the other range of assessments of composites that we can use, like thermography, acoustic monitoring, that are more widely used in industries such as the aircraft industry. Also, we've done quite a bit of strain gauging, not so much these days because Tony G alone have done over 200 projects now, so we have a lot more confidence than we did in the early days. There's still some challenges ahead. It's been, it's about 19 years now since we started out on the road in the UK of using composite materials to strengthen structures, and still it's a bit of a battle to raise awareness, just make people aware of the materials and what they can do. But we do have very good design guidance now, so nobody can use that as an excuse for not actually designing strengthening schemes with the materials. But we still need to guard against inappropriate use, despite there being good guidance available and lots of people with expertise to advise those who haven't got it. Still just occasionally do see people treating strengthening schemes with these materials as if it was steel on concrete. And one thing to mention is that applying the materials unstrained, without any post-tensioning, is going to have a minimal effect on the deflection of RC structure. And in those cases, if deflection is the thing you're trying to address, then a post-tension solution is one to go for, which Fabio will talk about. In terms of application on site, there is actually an accreditation scheme out there, but it's been very poor take-up just because of the recession we've gone in. The size of the market hasn't developed as we'd hoped. So in summary, we've got at our disposal a very strong lightweight strengthening solution, minimal visual impact, 19 years of usage in the UK. It's relatively low cost to install, extensively backed by research and development, and we've got world-leading expertise here in the UK.